So we've talked a lot about absorbing light. Now it's time to talk about fluorescence emission of light. So this section of the book is called What Happens to the Absorbed Energy? And well, there's several things that can happen, but we're going to ignore some of this for sure, and just focus on this part over here. So what I'm going to be doing from here on out is dancing between visuals and another slide where I will just write notes that you should be writing along with. Give yourself a full sheet of paper for this. And we'll start by replicating most of what's shown in this diagram here, while also trying to understand it better. So you should dedicate about a quarter to a third of the top of your paper for this drawing that we're about to make. And I'm going to start at the bottom of that drawing and just draw a thick, dark line like what we've seen in the past. I'll leave a little bit of space to the right for some extra notes. And I will label this line as S0, V0. So ground state for the electrons and the vibrations, and one more time that S just indicates that our electrons are anti-parallel. Every spin up has a spin down. And now, on the right half of this diagram, I will draw another thick black line, somewhat above, and we'll label this one S1, V0. We've seen this already in this lecture. S1V0 just means that this line represents an electronic excitation only. If energy is absorbed that's equal to this delta E here, an electron will go from the HOMO to the LUMO, but the vibrations will still stay at the lowest energy possible. And we'll make one other note about electronic transitions. We'll star this. This is why we gave ourselves some space to the right. Electronic transitions induces a shape change. Induces a shape change. Once that electron is in a different position of the molecule will change its shape to accommodate that new position. We'll see that in the visuals that I'll be presenting momentarily. But first, let's flesh out this diagram a bit more. Let's also imagine that there exists some vibrational energy state that's about equal in energy to that excited electronic state. But in this case, let's imagine that this level that I just drew represents no electronic excitation has occurred. All of that absorbed energy went into just exciting some very high energy vibration, and there are numerous vibrational energy levels underneath this. To just contrast these two different energy levels that are about the same in energy and thus would be reached by absorbing the same energy photon, on the left, what this represents is that our molecules at our ground state, all the electrons in the lowest energy position, vibrations at the lowest energy frequency, and then all of a sudden it absorbs this light, and it doesn't just intensify, it's like super intense vibration now, right? You can hear it in my voice, that fluttering vibration. And then over on the right side, what this represents is that the vibration doesn't really change at all. It's just that the electron takes that energy when it absorbs light and goes from one position to another position. And the result will be that the molecule itself will change shape to accommodate this position. Now, this concept that I've mentioned earlier called the Franck-Condon principle tells us that this transition is not happening. If light of this energy is absorbed, it's going to go into the electronic transition possibility. It's pretty much a zero chance that that energy is absorbed and the molecule reaches this extremely high vibrational state. Again, that principle is beyond the scope of this class, but just know that it tells us that this is not going to happen. That being said, we still acknowledge this energy level's existence for something that will come later. So for now, let's shift our attention to the right side of the diagram where the electronic excitation is depicted. And let's also draw some levels above that. And at this point, you should hopefully recognize what I'm drawing and what this represents, which are different vibrational excitation levels, but still within that same electronic energy level. So we'll label that highest level that I drew as S1, V3. So if light of this energy is absorbed, It will cause the molecule to not only experience an electronic excitation, but a third level vibrational excitation. If you don't know what I mean by that, please go back to the first video of this lecture and make sure that you get it. And so we will label this process as process 1, and then we'll make a note underneath the drawing, 1. What that arrow represents is a vibronic excitation from ground state, vibronic excitation from ground state, which I'll just label GS. And to give it its specific label, ground state would be S0, V0, as we see in our diagram. And we are transitioning to an excited state, ES. And particularly, this excited state is S1, V3. So let's look at a visual to go with that. So we're back to this slide. First, quickly notice that the diagram you drew is starting to look fairly like this diagram from the book here. And then let's add that label 1 to this diagram. And then this is just basically what you wrote, vibronic excitation from UV or visible light absorption. And two things are happening in the vibronic excitation. One, the electronic excitation occurs, which changes the shape of the molecule, as we noted earlier. For formaldehyde, the sample molecule we've been using for a couple of lectures now, that shape change involves going from a trigonal planar structure to a trigonal pyramidal structure. So when we're in the ground electronic state, we're trigonal planar. In the excited electronic state, trigonal pyramidal. But beyond just the electronic excitation, we also have that vibrational excitation on top of it. So our vibration goes from the lowest intensity energy vibration to a higher energy vibration. Now, none of this is new. We've covered this in the previous videos. This section is all about what happens next. What happens once that energy is absorbed? So let's write some more notes. Well, what goes up must come down. The molecule is not going to remain at this unstable, highly energetic state forever. It will eventually make its way back to ground state. But it won't do it all at once. It's going to lose the energy in a series of steps. The first energy loss will be the loss of this excess vibrational energy. Notice I'm using a squiggly arrow. I'll get into that in a moment. For now, I'm going to label this note 2. And then let's just write what that means. Vibrational energy is rapidly lost through collisions with other molecules. Let's write it, then understand it. Vibrational energy is rapidly lost through collisions with other molecules. And quickly ask yourself, what kind of energy is associated with collisions? And the answer is kinetic energy. And so this transition in the molecule is represented by the labels S1, V3, which is where we were after absorbing the light in process 1, going to S1, V0. So before moving on, I want to clarify two things. First of all, there is nothing special about that initial excitation to S1V3. I chose that arbitrarily for this example. I could have chosen S1V2 or S1V1. I chose S1V3. The second thing I want to clarify is what I mean by vibrational energy is lost through collisions. So imagine we have our excited molecule at this V3 vibration. And then this molecule bumps into another molecule, and the vibration slows down. Maybe we've lost some energy and gone down to V2. And in the meantime, the molecule that was bumped into has gained that energy in the form of kinetic energy. So now it's just moving around the solution a bit faster than it was. But back to our excited molecule. So here it was at V3, then it bumped into a molecule, vibration slows down, it's at V2. Maybe another collision brings it down to V1, And the final collision brings it down to our ground state lowest energy vibration possible, V0. We call this kinetic energy transfer among these microscopic particles heat. So we say that the vibrational energy is lost through heat, but we should know what that really means. It's these small kinetic energy transfers through collisions. And so let's put a visual to this. Process 2, vibrational relaxation to lowest vibrational level of the excited electronic state. So our molecule was vibrating like so, and by the time all these collisions are done, it's back to this lower energy vibration. But notice it's still in this trigonal pyramidal shape because the electron is still in its excited position. So now what happens? Well, there are two options, and I'm going to cover the more common process first. So I'm going to start at that S1V0 level and draw a squiggly line to that high energy vibrational state that was described earlier. And we are going to label that process 3, and we'll call that internal conversion, but first let me clear some space. And then write note 3, internal conversion. Once again, I'll just write what this means and then try to describe it better. The molecule enters the ground electronic level, but a high vibrational level of roughly the same energy. So molecule enters ground state, electronic level, ground state, electronic level, but high vibrational level, of roughly same energy. And so in this process, the molecule isn't actually losing any of this excited energy, it's just converting it into a different form. That's why it's called internal conversion. As the electron relaxes, that energy is put into exciting the vibrations until we get this high level vibrational state that's basically at the same energy as where we were before. And so visually we can represent this like so. Process 3, internal conversion. So here's our molecule where we left it. It's still in this excited electronic state where we're in this pyramidal geometry, but our vibration is as low in energy as it can be. But then internal conversion happens. The electron relaxes and the geometry goes back to the initial trigonal planar geometry, but our bonds are now vibrating at this extremely high speed. And so that's why we had to acknowledge the existence of this high vibrational level earlier, because the molecule winds up getting here after it's absorbed energy in the first place and it's trying to lose it all. Because once the molecule has converted that energy into vibrational energy, it can lose it through a series of collisions like what happened before. So it doesn't have to lose it all at once, it can lose it in steps, which is a lot easier. So this is the much more common relaxation method for the molecule after this has happened, is to convert and then collide and collide and collide until we're back to ground state. So let's add a bit more to our notes. We started at S1 V0, and then through internal conversion, int conversion, we reach S0 and this high vibrational state. Maybe it's V20, maybe it's V27, who knows. And then through collisions, not one collision, but a series of collisions, we can make it all the way back to ground state, S0, V0. And let's label this as being the common relaxation process. And we'll add those collisions to our diagram. One more time, using a squiggly arrow for this process. So what does this squiggly arrow mean? And why did the first arrow we drew just go up straight? So squiggly arrows mean that no light is involved, and straight arrows mean that light is involved. So this transition involved the absorption of light, But this relaxation did not involve any light being emitted, it was just collisions. This was just a conversion of energy. This was more collisions, so no light is involved in anything we've been drawing over here. But, as I said earlier, there are two options for how this electronic energy can be lost, and the other option does involve light. Specifically, the emission of light as the electron loses its energy. So it should stand to reason that if absorbing light can increase the molecule's energy, then releasing light can lower the molecule's energy. And we call this process fluorescence. Fluorescence is just the emission of light following an initial absorption of light. And so we'll just write emit energy as a photon. Emit energy as a photon. And so we just go from S1 V0 to S0 V0. And this is just from shining some light back out. So let's write photon emitted. We'll also note that it doesn't have to go all the way to ground state. It could actually end up at S0 V1 or V2, etc. I'll get into that later. Now I'm going to make a couple of side notes. First, note that the energy that will be lost by emitting light is lower than the energy that was initially absorbed from absorbing light, and that's because some of this absorbed energy was lost through these collisions. Only this energy can be lost in the form of fluorescence. The vibrational energy is guaranteed lost through collisions, no question. We will never fluoresce from this state. We will always start here. And so we'll note that this photon is lower in energy and thus longer in wavelength than the excitation photon. The other note I want to make is that processes 3 and 4 are competing. And process 4 is uncommon. So what's set in stone is the following. If light absorption causes a vibronic transition, this vibrational energy will be lost through collisions. From this state, the molecule has two options for losing this energy. One is the far more common internal conversion collision process, and the other is what we were just talking about, the far less common fluorescent emission process. While fluorescence is far less common in molecules, it's much more useful for analytical purposes because emitted light is something that we can detect, whereas collisions is not something that we measure or detect. And analytical chemistry is all about making measurements. So this process, while far less common, is also far more useful for our analytical purposes. So let's just put a visual to this and end the video. Process 4, fluorescence. The emission of photon allows the relaxation back to the S0 electronic state. So we emit, and then we're back to trigonal planar because the electron has relaxed. That relaxation may bring it all the way down to V0, or there might be some leftover energy in the form of vibrations, but that can be lost through collisions. I'll get more into this in the next video.